this, and here we go. All right, guys, there's your topic for today. So what you're going to find is that today is going to feel like sort of a catch-all. Of course, the pervading theme that's going to ride through all of this is polarity, intermolecular forces, things like that. But guys, today what we're going to do is we are going to talk about, first of all, why our water in Utah doesn't boil at 100 degrees Celsius. And we're going to probe that concept a little bit. Then what we're going to do is we're going to tie boiling back to intermolecular forces, and we're going to figure out what can we do to change the boiling point of water. And in order to understand that, we're going to have to dig into a concept about what happens when things dissolve. How do solutions form? And then once you understand that, we can then talk about how do solutions behave differently than the pure liquids from which they're formed. So guys, you don't need to write this down, but this is sort of our outline for the day in question form. So guys, by the end of the day, we're going to be able to answer, and some of these were questions that we asked the very first day of this unit, but we're going to answer these questions. So guys, why? In lab, the lab that you just turned in, remember the graphs you drew. When you heated the water, the temperature of the water went up and up and up, and then the temperature stopped changing. Let's review for the test. Guys, what was happening to that water when the temperature stopped changing? And don't say boiling. What was happening when the temperature stopped going up? Oh, that's boiling. What was happening to the molecules? The intermolecular forces were breaking. Now, guys, we understand that that should happen at 100 degrees Celsius. But if your water got, and I mean this seriously, if your water got to 100 degrees Celsius, you need to let me know because your thermometer is broken. Guys, water does not boil at 100 degrees Celsius. Did any of you get to 100? You guys did? When we do the next lab, which will be after, it'll be a while, I'll switch you thermometers. So just don't, well, you'll see. For the next two labs, we won't be using thermometers, but then the next one we will, and look at your thermometer and think to yourself, this is broken and we'll trade. So guys, we're going to answer the question, why does water not boil at 100? And it actually does boil at about 96. So then we're going to ask this question. Is there anything we can do here in Utah to get the water to boil at 100? And obviously the answer is yes, and we're going to talk about what those things would be. Then guys, after that, we're going to answer this question. Why is it, guys, that some things dissolve in water while others don't? And guys, if you've never thought about it, the question that we're basically asking is, what's up with this? Why is it that some of these are I's and some of these are S's? Why do some things dissolve in water while other things don't? And guys, understand, we're not going to give you the complete answer today. You'll actually have to come back for AP to talk about the complete answer, but I'm going to give you most of the answer. Why is it that some of these things dissolve in water while others don't? So guys, the reference for that is the soluble versus insoluble things on our solubility chart. Then we're going to answer this question. Why is it that we put salt on our roads here in Utah? And that's going to tie back actually to this because it all has to do with solubility and dissolving. So guys, that's our outline for today. You got the idea? You guys ready to go? All right, here we go. So guys, starting off, let's answer this question first. You may want to write this down in your notes. So guys, why is it that water boils at 96 degrees here in Utah? Well guys, I would propose to you, and you already know part of this answer, but I would propose to you that in order to figure this out, this is really the question that we need to answer, and this is where we're going. In order to understand why water doesn't boil at 100 degrees, what we've really got to figure out is what is it that determines the temperature at which water boils. But guys, you already know the answer to that, right? Put this together in your head. Well, maybe I should even remind you. Remember when we played this game and we talked about water and we talked about methanol? What temperature did water boil at? We said 100. Do you guys remember what temperature methanol boiled at? Was it above or below? Remember, this is the alcohol that I spilled on the table and it evaporated really quickly. So guys, did the methanol boil at a temperature above or below the water? It was below. And what was it about methanol that made the temperature boil below the temperature of water? Weaker intermolecular forces, because it's less polar. So guys, you already understand part of the answer to this question. One of the things that determines the temperature at which liquid boils is the strength of the intermolecular forces. The stronger the intermolecular forces, the higher the boiling point. But guys, that's not the complete answer. Because if that was the complete answer, water would boil at the same temperature no matter where it is. So guys, why does water boil at 96 rather than 100 here in Utah? Do you know? It has to do with altitude, which is a function of air pressure. So guys, let's talk about this. This is actually why water does not boil at 100 degrees Celsius here in Utah. It is a question of atmospheric pressure. I'm realizing I forgot to print my notes. So, I'm going to just pull them up on my phone. Oh yeah, you guys get to. Why shouldn't I? Okay, so guys, ready? What on earth does altitude and air pressure have to do with boiling point? Well, obviously, don't try to write this down. But guys, this is the deal. Ready? I really want you to do this. When you guys go to lunch today, because we all get an hour for lunch because we all get pride. You don't know how happy that makes teachers, because we never get pride. You guys, sometimes we never get an hour for lunch. It makes us happy. Okay, so guys, when you go to lunch today, here's what I want you to do. When you walk out the door, I want you to stop so you don't run into anything, and I want you to look up. And when you look up, what's the first thing you're going to notice? You're going to notice, oh my gosh, this air is really disgusting, right? Because the inversion is set in. But then, guys, if you squint really hard, you're actually going to be able to see blue sky through the yuck. But you know what you're actually seeing, guys? 60 miles of atmosphere. Did you guys know that? That between you, your nose, and outer space, there's actually 60 miles of atmosphere. So when we send spacecraft out of our atmosphere, they've got to be 60 miles off the surface of the Earth, because there's 60 miles of air between you and outer space. Now guys, here's the thing that you got to understand. Air is matter, and matter has mass, and mass gets pulled on by gravity, and therefore it has weight, and air is really heavy. Guys, this is crazy, and I'm going to show you the numbers in a minute, but guys, the numbers go like this. Imagine if we had a 1 meter, let me move this over, so a 1 meter by 1 meter space, okay, so it's basically this area right here. So guys, there's a 60-mile tall column of air sitting on this 1 meter by 1 meter space. Guess how much that air weighs? Take a guess. 5 pounds, 10 pounds. How much does the air weigh that's sitting on a meter by meter, a square meter of space? Guys, it's frightening. The answer is actually, the actual answer is right here. It's about 10,000 tons. So guys, if... Yeah, right. No, I know. So, but guys, that's a ton, right? That's a lot of weight. So, yeah, it's a ton. So what if we did a smaller thing, and I actually brought it up a little early. So guys, what does that equate to if we're going to something smaller like this? Because the answer is actually, what, 1,350 pounds. Guys, there's 1,300 pounds of air sitting on this piece of paper right now. So why isn't it ridiculous? Why isn't it like, and you can't hold up the 1,300 pounds? Because it not only pushes down, it also pushes up, because the air wraps around and pushes in all directions. You get the idea? So what does that have to do with boiling? Well, guys, let me get some water inside of a beaker, and I think all of a sudden this is going to make sense. So guys, just like we've got air pushing on the paper, we've also got air pushing on the water. There's 60 miles of air sitting on this water. So how much does the air weigh that's sitting on this water? Compared to 1,350 pounds, is it going to be more or less? Less, right? Because it's a smaller area. I mean, there's probably 10 or 15 of these in that area. And guys, the number is actually this. It's 88 pounds. There's 88 pounds of air pushing down on the surface of the water. But guys, here's the trick. This column of air is only pushing down. Why is it not also pushing up on the water? Because it can't get to the water through the glass. So the air is pushing down on the surface of the water, but it's not pushing up on the bottom of the water. It is pushing up on the beaker, but not on the water. So there's literally 88 pounds of air pushing on this water. So in order for the water to boil and jump out of the beaker, what does it have to do? It's got to push up against 88 pounds of air. You get the idea? So guys, why then does water boil at a lower temperature here in Utah? Do you see there's less pressure, and why is there less pressure? There's less air, and why is there less air? Because we're higher. So guys, think about it this way. Our elevation here in Utah is about 4,300 feet. Let's call that a mile. 5,200 is a mile. Let's call our elevation here a mile. So guys, if this beaker was at sea level, there'd be 60 miles of air pushing on the beaker. That's 88 pounds of air. Now, if we move this beaker to Utah, it's now a mile in elevation. So how many miles of air is now sitting on the beaker? Not 60. 59. We're a mile up in the atmosphere, so now there's only 59 miles of air sitting on the beaker. That has less weight, so there's less force on the water, so it's easier for it to jump out and boil, so the boiling point goes down. Does that make sense? Go ahead. Not faster, but at a lower temperature. Yeah, did you hear that? So guys, what happens if we go to the top of Everest, which is at 28,000 feet? It's basically 6 miles in the air. It's going to boil at even a lower temperature. We could figure it out. But actually, water at the top of Everest boils at such a low temperature that it won't cook your food. Yeah, have any of you had this experience? Have any of you camped above like 14,000 feet, like Kings Peak? I used to mountaineer a lot, and we used to spend a lot of time over 14,000 feet. And guys, even at 14,000 feet, which is basically 3 miles up in the atmosphere, your water boils at a low enough temperature that like if you're making rice or spaghetti for dinner, it takes forever to cook because the water doesn't get that hot. And it's even worse at the top of Everest. So what do they do to fix the problem? You guys know? I'll show you in a minute. But yeah, it actually, and at the top of Everest, you can almost put your hand in boiling water. I mean, you wouldn't leave it in there for long, but you could put your hand in boiling water and it wouldn't immediately scald you. Okay, so guys, you get the idea, the connection between altitude, pressure, and boiling point? You okay? Okay, so guys, with that said then, let's bring in the thing you already know. So here's what we know now. We know that atmospheric pressure determines the boiling point of a liquid. The lower the atmospheric pressure, the lower the atmospheric pressure, the lower the boiling point. Does that make sense? But guys, what's the other factor that determines boiling point? And you already know this, so I'm just going to give it to you. It is intermolecular forces. So you may want to write this down. The idea that higher altitude results in lower atmospheric pressure and therefore a lower boiling point. And we should probably add the word pressure in there. This is killing me not having my notes. I don't know, but I'm going to print them. Okay, so let me bring this back up while that prints, and then we'll be good. So guys, if you didn't figure that out, that's the connection. The higher the altitude, the lower the atmospheric pressure, and therefore the lower the boiling point. And then, guys, as we said before, we also know the other factor that influences boiling point is the strength of the intermolecular forces. And I think you well, maybe I should ask it as a question rather than give it to you. So guys, what's the connection between intermolecular force strength and boiling point? Is it a direct or an inverse relationship? As intermolecular forces get stronger, what happens to the boiling point? Higher or lower? Higher. Good. So if you don't remember that, guys, you may want to write that down. Remember the idea that stronger intermolecular forces lead to higher boiling points. You guys okay? Okay, so now, guys, we understand that there are two things that influence the boiling point of a liquid. One of them, as we knew before, is intermolecular forces. The other is atmospheric pressure. So now, guys, we can ask the follow-up question to all of this. We now understand why water boils at 96 Norum, higher altitude, lower pressure, lower boiling point. The question then becomes this: is there anything we can do to make water boil at 100? And of course, we know the answer is yes. The question is really what? Guys, what could we do to make water boil at a temperature higher than 96 or make it boil at 100? So guys, let's pick this apart one at a time. Let's talk about atmospheric pressure first. So if we want water to boil at a higher temperature, do we increase or decrease atmospheric pressure? Increase or decrease? And guys, again, this is the stuff you're going to see that on the test. If you want to increase boiling point, what do you do to atmospheric pressure? What's the answer? Do you increase or decrease it? You increase it. So guys, now the question becomes how? How do you take a beaker of water and increase the atmospheric pressure on it? Well, guys, the first way is kind of cheating. If we wanted to make this water boil at a temperature higher than 96, one of the things that we could do with this is take it on vacation. You take this down to San Diego, which is at sea level, and what happens to its boiling point? It goes up to 100. But guys, that doesn't really answer our question. One of the things we could do, and you should write this down because technically it's true, we could make the water's boiling point go up by decreasing the elevation, take it down to sea level. The problem is then it's not really an Orem anymore, and that doesn't really meet the question. But there is a way to answer the question. Guys, what could we do here in Utah to increase the atmospheric pressure and thereby increase the boiling point? What do we use? Come on, you guys live in Utah. You all can food. It's a law. You also eat green Jell-O with carrots. Don't know why that's a law. But, guys, we all do this. When you can food, what do you do to the jars before you put your food in them? You boil them. Why do you boil them? To kill the bugs. But guys, some of you actually do this right, and you don't just put the jars in boiling water. What do you put the water and the jars in? Look familiar? What is it? It's a pressure cooker. Guys, why do we use pressure cookers? Well, the answer's in the name. So how does a pressure cooker work? Well, guys, the idea is this. In the bottom of the pressure cooker, oh, come on. There we go. In the bottom of the pressure cooker, we've got some water. And you allow the water to boil. Now, if water boils in a beaker, the steam just goes away. But a pressure cooker has got an airtight lid. So when the water boils and goes up here, where does the steam go? Nowhere. It stays in that small space. And as that steam enters this small space, you get more and more steam in there, and it makes the pressure go up. And as the pressure goes up, the pressure actually pushes back down on the water, increasing the pressure on the water, creating an artificial atmosphere with a higher pressure. And what happens to the boiling point? It goes up. You get the idea? And guys, that's why you put your glass jars in there. It allows the water to go to a higher temperature, which kills more of the germs. Yeah? So the other thing that we could do is use a pressure cooker, and a pressure cooker would also increase the boiling point of the, or increase the, the boiling point of the water. You guys also understand that there's something exactly like a pressure cooker in your cars? Not your engine, your radiator. Guys, on the top of a pressure cooker, there's a little valve that keeps all the steam and the water trapped inside. On top of your radiator, there's a cap that screws and locks on and keeps the water in the antifreeze inside your radiator. And it's actually a pressurized cap that creates an artificial pressure that lets the water rise to a higher temperature. So what happens if you drive your car for 50 miles, heat up all of the engine and the radiator, and then you screw the lid off? Why does it explode? Think through it. When you screw the lid off, what happens to the pressure? Pressure goes down. What happens to the boiling point? The boiling point goes down, and now all of a sudden, all of that radiator fluid can boil, and it comes out like a geyser. That's also the way geysers work. You should look that up too. Okay, so you guys got the idea? Atmospheric pressure boiling point. You good? Okay, so now guys, let's try the other side of this. What is the other thing that we could do to increase the boiling point of the water? And guys, the answer, interestingly, is strengthen intermolecular forces. So guys, if we could take the water inside this beaker, and if we could make the intermolecular forces stronger, what would happen to the boiling point? It would go up. So guys, what on earth could we do to this water to make the intermolecular forces stronger? Well, we can't make the molecules more polar. So what could we do to this water in order to make the boiling point go up by strengthening intermolecular forces? Add salt. Guys, if you dump salt in here, the boiling point will go up above 96. You dump sugar in here, the boiling point will go up above 96. But if you dump sand in here, the boiling point will not change. So what do sugar and salt do that sand don't? That sand doesn't? Dissolve. Guys, anything that will dissolve in here will make the boiling point go up. So the other thing that we could do to make the boiling point go up is actually create a solution. So guys, how does this work? And this is how we're going to finish the day. How is it that creating a solution makes the boiling point go up? Well, guys, in order to answer that, the first thing that we've got to do is we've got to remind ourselves about the parts of a solution. Remember the day you learned about the triangle, hetero, homogeneous, all of that happy stuff? Guys, you remember maybe that solutions have two parts. You've got a solute and a solvent. And if you don't remember that, you may want to write it down because we're going to be using those terms. So if we're thinking about salt water, the salt is the solute and the water is the solvent. And so guys, the question then becomes this. Why is it that adding salt to water or adding sugar to water makes the boiling point go up? Well, you're going to find out that it all has to do with intermolecular forces. The question is why, and that's what we're going to explore for the rest of the day. So guys, you don't need to write down the last bullet point here, but basically the idea is this. To understand why it is that creating solutions makes the boiling point go up, the first thing that we've got to figure out is how does dissolving happen in the first place? So if we come along and if we grab some salt and if we've got our water and if this water boils at 96, and now I add some salt, and when I stir this, as the salt dissolves, the boiling point goes up. The question is why? And the answer to that question is what is happening when the salt dissolves. So guys, what we're going to do for the rest of the day then is talk about dissolving and how dissolving works, and then connect it to intermolecular forces and boiling point. You ready to go? So guys, how does dissolving work? Well, I'm going to show you in a minute, but I need to share some terminology with you first. So guys, to do this, we're going to answer this question. Why do some things dissolve in water while others don't? And guys, the answer to this is actually a lead-in to how dissolving works in the first place. So why is it that some things dissolve and others don't? Well, guys, the answer is this, and you want to write this down word for word. This guy's important. Comes down to this. In order for a solute, like salt, in order for a solute to dissolve in water, the water molecules, which are polar, have got to be strongly attracted to the stuff that's dissolving. So guys, in order for dissolving to happen, the water molecules, which are polar, have got to be strongly attracted to the stuff that's dissolving. So guys, the question then becomes this. If water is polar, what kind of things would water be attracted to if water's polar? Well, the answer, guys, is other polar stuff. Polar water molecules will be strongly attracted to other things that are polar. So it basically comes down to this. What this means is that if a substance dissolves in water, it's got to be polar, like salt and sugar. Those are very, very polar substances. So what about things that don't dissolve in water? What's got to be true of those? They're not polar. So oil, gasoline, things like that. Guys, those things are not polar, and therefore they don't dissolve in water because the water molecules are not attracted to them. So guys, the bottom line is this. Why do some things dissolve in water while others don't? Well, it goes like so. Water molecules are polar. So for something to dissolve in water, the water has got to be strongly attracted to it. And I'll show you a video of this in a minute. But guys, the question then becomes, what is it that water is attracted to? And the answer is other polar things. So if something dissolves in water, that thing's got to be polar, like salt and sugar and things like that. And then if a substance doesn't dissolve in water, that means water's not attracted to it. And the reason water's not attracted to it is because it's not polar. So guys, this is the big idea of the day. Let me let you write it down. Ask questions if you need, and if not, I'm going to show you some videos. Actually, I'm going to show you an animation and then a couple simulations for what this actually looks like. So do you feel like you're getting the idea? Why do some things dissolve and others don't? It's all about polarity. Polar things dissolve in water. Non-polar things don't because the water's not attracted to it. You guys good? Okay, let me show you this in video form. So guys, this is kind of what this looks like. But guys, understand this is an animation and not a simulation. This is like a cartoon. But in cartoon form, this is what dissolving looks like. So we're going to throw some salt in water, and this is how it dissolves. So guys, there's our salt crystal, right? What's the blue stuff represent? Water. So we've got salt in water, and along come the water molecules. And guys, these water molecules are moving around rapidly. It's like a mosh pit inside there. And these water molecules just run into the salt crystal. And when they do, look at what happens. These water molecules drag the salt ions off of the crystal and off into solution. So guys, let's make sure we're clear about this. What are these, and I'm going to go white. Guys, what are these forces of attraction that draw the water molecules up against the salt ions? Those are intermolecular forces. So these water molecules are attracted to the salt ions by intermolecular forces. And these intermolecular forces are strong, and they cause the water molecules to stick to the sodiums and the chlorines. And the water molecules literally pull the salt crystal apart because those attractions are strong, and it draws the ions off into solution. And eventually you end up with this, where the negative ions are surrounded with water molecules. The intermolecular forces are here. The positive ions, notice the water molecules flip around because of their polarities. But guys, you've got the water molecules surrounding the ions, and that's what it looks like inside of a solution. You get the idea? Yeah. Well, this isn't quite dissolved yet. So what if we did this? What could we do to make the salt dissolve faster? Heat it up. Why would this go faster if the water was hot? Yeah, the molecules are moving so much faster, which allows them to run into the crystal and break it apart quicker. So how long it takes depends upon how much salt there is and how hot the water is. The hotter the water, the faster the collisions, the quicker it dissolves. Does that make sense? Hey. Everyone else is done with the lab. So, guys, but you understand this, right? This is an animation. This is really not what it looks like when salt dissolves. So, guys, let me show you a simulation, just like the simulations I showed you last time. They're slowed down, but the idea is this is really what it looks like. So this is what a salt crystal looks like. Let me go back. The ions all locked in place, and they're sitting there and they're wiggling, and in comes the water molecules, and these water molecules grab a hold of the salt ions and rip this thing apart and carry these ions off into solution. And again, guys, the intermolecular forces there are strong. The water is strongly attracted to the ions, and it drags those ions off into solution. So then, what does the solution look like? Well, guys, this is actually what salt water looks like. There's the mosh pit. You've got the water molecules all bouncing around. And then you can see the ions that are like tucked. Literally, these ions are like tucked up inside of the solution. And so you've got the water molecules moving around with the ions stuck inside of the water molecules. The intermolecular forces hold the ions to the water molecules, and that's how a solution forms. Do you get the idea? So guys, literally when the solution forms, it literally looks like this. I love these things. I just bought these this year. So guys, this is our mosh pit, right? This is our water. These molecules are all moving together. Guys, what holds these molecules together, reviewing for the test? Intermolecular forces, and they're free to move, and they can go wherever they want. Every now and then they jump out, which we call what? Evaporating. But guys, remember, these things aren't boiling for two reasons. One, air pressure, and two, the intermolecular forces. So for them to boil, they've got to break the intermolecular forces and push up against air pressure. Now, let's dissolve some salt. Let's dissolve some salt into the solution. So now we put this in here, and now we've got some ions in there, and now these ions are all tucked inside of there, and they're still mucking around, and they're still doing their thing. But guys, here's the point. When we add the salt to the water, what does that do to the boiling point? Does it go up or down? It goes up. Do you now see why? Guys, why would this be harder to boil with the salt ions in the water? Let's talk about it. And that's how we're going to go to finish this up. So guys, the question now becomes this. Why does the boiling point go up? So guys, to answer that question, we need to answer this question. What effect does the salt have on the water? When we dissolve the salt in the water, how does that impact the behavior of the water? And guys, to answer that, what we're going to do is this. Don't draw these, but we're going to look at this a couple different ways. So here I've got 3 beakers. And guys, here's what I'm going to do. In one of these beakers, we are going to put, I lost an ion. Oh, there it is. Guys, in one of these beakers, we are going to put pure water. And we're going to talk about what does pure water have to do to boil. Then in one of the other beakers, we're going to show you salt water. And then in one of the other beakers, I'm going to show you sugar water. And we're going to talk about how the salt and the sugar change the behavior of the water. So you guys ready? This one you should already know. Let me grab a pen and let's talk. So guys, let's look over here at, I'm going to go blue. Let's look over here at pure water. So guys, in pure water, what has to happen for that water to boil? What holds the water together? What holds the water together? Intermolecular forces. So we've got all these forces of attraction that hold all the molecules together. They're all attracted and they're mosh pitting. So guys, in order for this to boil, assuming that air pressure isn't a factor, but in order for this water to boil, what has to happen to those intermolecular forces? They got to break, right? So these intermolecular forces have got to break and the water jumps out and it boils. Now look at salt water. So guys, look at what's going on. Just like you saw in the videos, the water molecules are oh, that was cool. I guess I got too close. The water molecules, guys, are attracted to the salt ions. So we've got all these forces of attraction between the water molecules and the salt ions. Now, guys, here's the question. What do you know about these forces of attraction compared to these forces of attraction? Are the attractions in the salt water stronger or weaker? How do you know they're stronger? This is good logic. How do you know those forces of attraction are stronger in the salt water? What if they weren't? The salt wouldn't dissolve. Do you get it, guys? Remember what we said. The water has got to be strongly attracted to the salt. So we know that these forces of attraction are stronger than these forces of attraction, because if they weren't, the salt wouldn't dissolve. So guys, if these attractions, I'm going to clean this up, if these attractions in here, if those attractions are stronger, and we know that they are because the salt dissolves, guys, if these attractions are stronger, will they be easier or harder to break? Harder to break, and if these are harder to break, it makes the boiling point go up. Do you get it? So guys, follow that logic. Here's the idea. Inside of pure water, here we've got pure water, and inside of pure water, the intermolecular forces have got to break for it to boil. Well, guys, the same thing's true over here. The intermolecular forces have got to break for this to boil, but now the intermolecular forces are not just water to water, they are also water to salt. And what do we know about the water to salt intermolecular forces? Stronger or weaker? How do we know they're stronger? Because the salt dissolves. If they weren't, it wouldn't dissolve. And if these forces are stronger, they're harder to break and the boiling point goes up. Do you get it? So now let's do it with sugar. Guys, this is actually what a sugar molecule looks like. It's a big old chain of carbons and hydrogens and oxygens all balled together. But guys, the same thing's going on here. These water molecules are strongly attracted to the sugar molecules. How do we know they're strongly attracted? Because it dissolves. And guys, if these molecules are strongly attracted, these forces are harder to break, and what happens to the boiling point? It goes up. Does that make sense? So guys, let's summarize it this way. This has a name, and this is your last page of notes. Guys, the name for this is or are what are called colligative properties. Guys, colligative properties are properties of solutions that are determined by how many particles are dissolved, by how much is dissolved, and not what type of stuff is dissolved. And guys, that's the thing that's cool about this. It doesn't matter if you dissolve sugar, salt, lawn fertilizer. It does not matter what you put in the water. If it dissolves, the boiling point will go up. And the more that you add, the more the boiling point will go up. And these are what are called colligative properties. Now guys, there's like a dozen different colligative properties. You only need to know 2. So the first colligative property that you need to know is what we call the boiling point elevation property. But we already just talked about that. When you add salt to water, the boiling point elevates. The boiling point goes up. Guys, the question is why? Why does the boiling point go up when you add salt to water? Somebody string it together. It's 3 logical steps. How does it go? Step number 1, if the salt dissolves in the water, what has to be true? The intermolecular forces are stronger. Thought number 2, if the forces are stronger, are they harder or easier to break? Harder to break. If they're harder to break, what happens to the boiling point? Goes just like this. So guys, the 3 ideas go like this. If the solute dissolves in water, the IMFs are stronger. Therefore, they're harder to break. Therefore, the boiling point goes up. Just like so. Does that make sense logically? So I'll let you catch up. We got one more thing to talk about, and then we'll look at your homework. Are you guys all caught up? You okay? Not quite yet. How about now? So guys, now we get to answer the question that we asked very last, the very first day of class in this unit. Why do we put salt on our roads here in Utah in the winter? What does it do? Okay, so it dissolves. And what is that? Why is that a benefit to us? What does it do? Actually, not bad. No, that's so guys, if you don't understand, and actually Enix's right on it, but let's make sure you all understand. So guys, what we're going to do now is we're going to talk about what is called the freezing, and you may as well write this down with me now. This is called the freezing point depression property. And Enix's right. When they put salt on their roads, it causes the ice to break apart. And I love that he mentioned that that's breaking intermolecular forces. But guys, let's explain what's going on. You ready? You may want to write this down with me. Here's a temperature scale. And this is going to be in degrees Celsius. So guys, at what temperature does water freeze in Celsius? No, freeze. 0. So guys, this is the freezing point of water. 0 degrees Celsius. Now understand, this is not Fahrenheit. Water freezes at 32 Fahrenheit. This is Celsius. So imagine that it's 25 degrees Fahrenheit outside. Okay, that's below freezing. That's about -4 Celsius. So 25 degrees Fahrenheit, about -4 Celsius. Will the water on our roads freeze at -4 Celsius? Yeah, because it's below 0, right? So if it's below 0, if it's below 32, the water on our roads will freeze, it turns to ice, we hit the ice, our cars lose traction, and bad things happen. So guys, what do we want to do in order to take care of that? Well, we would rather the water be a liquid than a solid. So what we need to do is we need to figure out a way to get the water to remain a liquid at -4. So if we could do this, if we could take the freezing point of water and if we could drive it down to like -10. If we could take the freezing point of water and drive it down to -10, now -4 is no longer below the freezing point and the water melts and it's liquid and that's fine. So guys, that's actually why we put salt on our roads, is it decreases the freezing point of the water so that it can get colder without the water freezing. You get the idea? So the question is this: why would adding salt to water make its freezing point go down? Well, guys, I don't know if you know this or not, but it's really interesting. So here we've got water. And in order for water to freeze, what does it have to do? Well, it's got to move slowly enough that it can lock together and turn into this. Guys, this is actually what it looks like inside of an ice crystal. So these water molecules have got to slow down enough that they can all lock together in this ordered, repeated structure and turn into ice. Now, guys, here's the thing. Imagine if, my beaker, oh crap. My beaker broke. I'm afraid if I push on this, all right, I'm going to risk it. Rachel, you'll be fine. So, guys, imagine if instead of freezing water, imagine we were freezing salt water. Do you guys know about this? So if you freeze salt water, where does the salt fit into the ice? It doesn't. When you freeze salt water, the salt actually gets left behind. The salt does not fit into the ice. So in order to freeze salt water, these molecules let go of the salt and grab a hold of each other and freeze. So the ice gets left behind. And if you don't, try this at home. Take some salt water, like take a glass of salt water, and not a ton of salt, but enough salt that you can taste it. Take a cup of salt water, throw it in the freezer, and let it freeze, and then lick the ice. You won't taste the salt. Guys, the salt does not get trapped into the ice. It actually settles to the bottom. And so the salt doesn't get trapped in the ice. So the idea then is this. In order for this water, could you hold that for me? In order for this water to freeze, the water molecules have got to be able to break free and come over here and freeze, right? Well, guys, what do you know about the attraction? What do you know about the attraction between the water and these salt ions? Is it strong or weak? Strong. How do you know it's strong? Because the salt dissolves. So guys, if this attraction between the salt and the water is really strong, and if the water has got to let go of the salt in order to freeze, if this attraction is stronger, you've got to cool it to a lower temperature to get the water to let go of the salt and form ice. Does that make sense? So guys, that's why the freezing point goes down, because the water is tightly attracted to the salt, which makes it harder to let go and come over here and freeze. Does that make sense? So guys, let's summarize that. So it goes like this. So the idea then is that the freezing point goes down. And why does the freezing point go down? Well, it goes like this. If the solute dissolves, we know the intermolecular forces are stronger. If the intermolecular forces are stronger, it makes it harder for the water to get together and form structure, and as a result, the freezing point goes down. Good night. We got to get rid of that beaker. That could have been a disaster. So guys, there you have it. We now know why water doesn't boil at 100 in Orem. We now know what we could do to get water to boil at a higher temperature. We know that one of those things is add salt. So now we understand what happens when salt dissolves in water, and now we understand that when salt and other things dissolve in water, it makes the boiling point go up, and we understand why, and it makes the freezing point go down, and we understand why. So guys, that's how we're going to wrap up this unit. Except for one little tidbit that you might find helpful. So guys, we understand that when you add salt to water, it makes the freezing point go down, right? What if you add sugar? Will that make the freezing point go down? Yeah, anything that dissolves will make the freezing point go down. So why do we not put sugar on our sidewalks in the winter? Because it's nasty. But guys, what's the problem with putting salt on our sidewalks in the winter? Have any of you had this happen? You put salt on your sidewalks and then spring comes around and your grass is dead? Because salt kills your grass. So guys, I have a little suggestion for you. Don't put salt on your sidewalks. Put lawn fertilizer. If you spread lawn fertilizer on your sidewalks, will it dissolve? Yeah, lawn fertilizer dissolves in water. Will it make the freezing point go down? You bet. Because the thing that's nice is then when it melts and goes into your lawn, it doesn't kill your grass, it actually feeds your lawn, and so you get the benefits of both. If you're going to do that though, guys, make sure you don't get fertilizer that has iron in it, because the iron will actually stain your sidewalks. But if you can get iron-free fertilizer, spread that on your sidewalks rather than salt. It makes the ice melt and it feeds your lawn. Huh? Yeah. Oh, yeah, right. So, yeah, we didn't talk about that. So, guys, do you remember when we talked about this at the beginning of class? Why do they not put salt on the roads in Wyoming? Do you know? And that, okay, yeah, so that's why they sand the roads in Wyoming, because the sand gives you traction. It actually grinds down into the ice and gives you traction. But it still leaves the other question, why do they not put salt on the roads in Wyoming?
Because the horses would go into the road.
The horses would lick the salt and they would get sick. If I cared about Wyoming, I would be offended. No. Why do they not put salt on the roads in Wyoming? Do you know? Exactly. They can't add enough salt to drive the temperature low enough to get the roads to melt because it's so ridiculously cold in Wyoming. They could put salt on the roads until it was piled up a foot deep and it still wouldn't make the ice melt. So rather than try to melt the ice, which they can't because it's too cold, they just spread sand on the road. So rather than get rid of the ice, they just make it more traction-y. There you have it. So guys, we are done. Let me stop recording.